in the last class we understood how do we define the vectors, their algebraic representation and geometric representation. Vectors can be also defined by considering the rotation of the coordinate system, and that definition led to the transformation equations of this nature. Suppose you have a vector represented by ax and ay prime. Then you have a transformation equation that is ax prime is equal to ax cos phi plus ay sin phi plus ay prime is equal to minus ax sin phi plus ay cos phi. Right? Now we define ax and ay as a component of vector ay, and we define that if you transform the vector, so you have a prime coordinate system and unprime coordinate system. So if you go from a bar to a prime bar, which is basically represented by this component ax prime and ay prime. So we define that a bar is a vector if under the rotation of the coordinate system with angle phi, its components, which are the new components in the new coordinate system that is rotated by the angle phi, satisfies these two equations which we call as transformation equations. Right? Now this is called as the form invariance, or also called as a covariance. Remember, this notion of form invariance and covariance will appear at various situations. So this is the form invariance and covariance when the coordinates are rotated. Fine. If they don't have this form invariance or covariance, then you can say that this vector do not form a vector. So another way that we define a vector is the one which shows the form invariance or covariance under the rotation of the coordinate system. This has a very large implications when we come to the defining vector spaces. So component of a bar in particular coordinate system constitute the representation of a bar in that coordinate system. Okay. Transformation relations are the guarantee that entity A is independent of the rotation of the coordinate system. Now can we extend this case for 3 dimensions or 4 dimensions or any other dimensions? So answer is yes, and that is what we try to do. So we define that x, so we say that we will use more compact notations, and the compact notations are, say, x is equal to x1 and y is equal to x2, and you define a11 or the coefficients as cosines and hence for transformation equations, which are transformation equations for the coordinates, that is x prime y prime, which is x cos y plus y sin y, or minus and minus x sin y plus y cos y. These equations can be written in terms of this a11, a12, a21, and a22 as x1 prime is equal to a11 x1 plus a12 x2 plus x2 prime is equal to a21 x1 plus a22 x2. Fine. The coefficients a11, a12, a21 or a22 are interpreted as a direction cosines. Okay. So direction cosines, where you write down a12 as cosine of the angle between the positive x1 prime and x2, which essentially is sine phi. Remember, while considering this, we have a coordinate systems. X 1 x2, it is rotated, that is x1 prime and x2 prime, and then its rotated is with this angle. And you have a vector r1 whose coordinates are basically x, y in prime coordinate system and x prime y on prime coordinate system. So by simply using similarly x2 prime x1, which is equal to minus sin phi, we can just see that cosine of angle between these coordinates, positive coordinates, positive axis, is basically sin phi and minus sin phi. Similarly, you can see that a11 is equal to cos phi and a12 is equal to a22 is equal to cos phi. Okay. Now, interesting thing here is that we can write down this using the new notation, using the summation symbol. So we can write down xi prime is equal to. So we are more interested in writing down these two equations as a single equation using the summation conventions. So we use sum. Now we are summing over an indices which is j. So j goes from 1 to 2, where I is basically I is 1 and 2. Right? This makes sense?
Yes, sir.
So we can now see that I is a parameter that gives rise to one equation when it is set equal to 1, and another equation when you set I is equal to 2.
So in that case, subscripts or dummies I and J not equal. When
So here J is basically repeated indices, which we can also call the dummy index, is summed over. So I corresponding to 1 gives one equation, I corresponding to 2 gives you two equations where you are summing over J from 1 to 2 in order to get the transformation equations. So this is a summation index or dummy index that we are using it. So remember, when you have a dummy index, means you can replace this index by any other index. Doesn't matter. You cannot replace this. If you are replacing, then it will be on the right hand side. Now, you can generalize this to 3 or 4 or n dimensions. So we are interested in generalizing n dimension. How many dimensions we are now dealing is we are dealing right now we write down this transformation equation considering only two dimensions. Now how does this allow us to generalize to the n dimensions? You can say that you are defining a vector v which has n components. So n quantities, you can say Vj, that is a vector of
so in that case, the dummy index J would be summing over 1 to n.
Yes, exactly.
For in case of n dimensions.
Exactly. So now you define a new vector, that is, say, vector v bar, and now this vector v bar is a vector only and only if it satisfies the transformation equations. So how do you write down the vector v bar in n dimensions? So vectors v bar in n dimensions will be a vector if it satisfies the transformation equations, which again have this cosines aij and vj. The only difference is you are summing j from 1 to n, where your I goes from 1 to n. So you have multiple components of the vector. So if you say have 4 dimensions, you will have 4 components, correct? It is more like you can say that you have 4 projections. Like you can see here, you have 2 projections, ax, ay, and ax prime, ay. Here, how many projections you have? You have n number. So, what is this? We'll come to that. Now, aij again, here is the cosine of the angle between xi prime and xj prime. So you can consider n is equal to 2, 3, 4, 5, 6, 7 up to n. You can say that when you talk about n dimension, it's a space which is n dimension. Of course, we can't imagine more than 3 dimensions, but we can define a vector in more than 3 dimensions. That is the advantage of defining the vector in this setup where we consider a vector only if it has a form invariance with both variables under the rotation of the coordinate system. So you understand that rotation of the coordinate systems has enabled us to define a vector in higher dimensions. Okay, so you can see as we know that Aij defined as a cosines of the angle between positive xi prime and xj prime, correct? That is true. Here Aij so from this definition we can also write Aij as dxi prime upon dxj. There we are writing down the cosines of the angle between the positive xi prime and xj prime. Now you can consider this as x1 and x2. So you have unprimed and primed coordinate systems. So we are just writing down this as a writing down it in terms of the partial derivative. Now, suppose if you use the inverse relationships, that means you want to go from say prime coordinate system to the unprimed coordinate systems, you use the inverse transformation relationships. So inverse transformation relationship can be obtained by simply setting phi is equal to phi to minus phi, and in that case you will yield the equations of this form. Xj is equal to Aij xi prime, where j is sum from I is sum from 1 to 2. Or you can say that dxj by dxi prime is equal to Aij.
Sir, please do the dummy index of summation over I to n. I mean, in order to more generalized case.
Summation?
Dummy index
Yes.
will be summation from 1 to n for in or n dimensional generalized case. So
No.
rather than 2 dimension.
No. So right now we are specifically trying to write down our vectors using this definition. Okay? That means this is when you are trying to write down the xi and xj prime. This is the vector I already defined in 2 dimensions. This is the vector I am defining in the n dimensions. Okay? That is the difference. Okay? So we can use these 2 equations. Only thing is that these equations are giving me the cosines of an angle between the 2 axes in terms of the partial derivatives. I can use this partial derivative here that time, because when I am defining the vector in n dimensions, then the summation will be wrong.
Now the format is will remain same, but then you only change the notation only. For example, in 2-dimensional you wrote x, and in n dimension you wrote b.
So now let me write down this vi prime using our new forms of cosines in terms of the partial differentiations of the xi primes and xj primes. So I can write down this as a summation of dxi prime upon dxj into bj. Now here the summation is from j goes from 1 to n. Okay. Also we know that aij can be also written in this form, that is xj upon xi prime, wherein partial derivative of xj with respect to xi prime. So I can also write down this in this form, dxj dxi prime bj, where j is the summation going from 1 to n. Okay. Remember, the convention or the form of aij has been obtained by starting from the simple case of the 2 dimension, and we are trying to extend the case for the n dimensions. Correct? Now remember, there is one more important thing, that these direction cosines aij's that you see here, they satisfy something called as the orthogonality relations. So I will erase this part.
Sir, I already noted down everything, you can erase all.
Yeah, but I want some parts to be there on the board. Okay. Now let's see that direction cosines a and j satisfies and orthogonality conditions. Okay, what is the orthogonality conditions? aij is equal to delta j, where you are summing over the repeated index, is dummy index I, or equivalently you can write summation over AJI AKI is equal to delta JK. Now
You in that the second one you just only interchange the dummies.
yes, I am just interchanging them, but remember here that if I interchange, this is delta JK, this again you get delta JK.
And delta jk is the Kronecker delta function, right?
So delta JK is the Kronecker delta. And how do you define the Kronecker delta? Delta JK is equal to 1 for j is equal to k, and delta JK is equal to 0 for j is not equal to k. Now interestingly, that we are basically going to get the conditions corresponding to the suffix j and k's or indices j and k's. Now you can check this by simply using the aij that we have defined, that is a11, a12, a21 and a22 in two-dimensional case. If you use these conditions, it is more like you are finding the doing the cross product of the matrix that you write, and you get the identity, that is sin square theta n. So you can check for two dimensions. This will give sin square phi plus cos square phi is equal to 1. When you set j is equal to k, so this should give 1. When j is not equal to k, it should give 0.
Sir, in the orthogonality conditions, the summation dummy index will be sum over 1 to n, right?
Yes. So I index is basically is a repeated index, and in this case it is a number of dimensions. Now, in order to verify this equation in a general form, we can also verify it using the forms that we have for aij in terms of the partial derivative. So how you will write aij? We already have aij. How you will write aik? You can also write aik in a similar fashion. So I just use these two forms of cosines in order to verify these two. So how do I verify these two? I just substitute for aij, that is dxj by dxi prime. I substitute for aik from the second equation, that is dxk upon dxi prime, which is also equal to aji, aij and aji, and that is summation. Now here the summation is over I, that is the index, dxj upon dxi prime, dxi prime upon dxk. So you have, which is equal to dxj upon dxk. Okay? Now you can see that this is equal to dxj by dxk, where when xj is equal to k, it will give you 1. Otherwise, it will give you 0. Now, why it will give you 0? Because remember that these two vectors, two coordinates are orthogonal. They are perpendicular to each other. Okay? So,
Sir, what is the condition for orthonormality?
xj for dxa is equal to delta jk. So since xj and xk are the coordinates, when j is not equal to k, are assumed to be perpendicular, and in that particular case, when they are assumed to be perpendicular or orthogonal, right? So these conditions for orthogonality is purely being arrived from our cosines. So condition for orthogonality is basically that these two cosines should satisfy these two equations. Correct? That is the condition for the orthogonality. Now this clearly shows that delta Jk is equal to 0 when j is not equal to k. It says that we assume that xj are perpendicular, xj and xk are assumed to be, remember this is assumed to be perpendicular or orthogonal. Correct? That makes sense? Now so we have a vector defined in more than 2 dimensions. We know that you can write down these in terms of the partial derivatives, the cosines. You can prove that this satisfies the orthogonality conditions. So these are the orthogonality conditions that tells you that these vectors that we are considering are perpendicular orthogonal. Now we can again imagine a perpendicular Cartesian coordinates, but we cannot image more than 3-dimensional vectors, more than 3-dimensional space. But remember that we are able to define a n-dimensional space purely by starting from our definition of vector as the invariance, form invariance of covariance under the rotation of the coordinate system. So purely the new way of defining a vector in terms of the form invariance or covariance under the rotation of coordinate system enable us to generalize it to more than 2, 3 and 4 dimensions, and to enable us to introduce an n-dimensional space. Now, redefining the vectors in terms of the how its components are transformed under the rotation of the coordinate system, we need to emphasize 2 points here. The first point is this definition is developed because it is useful and appropriate in describing our physical world. Now, how it will be appropriate and useful we will come to see. Remember, our vector equations are independent of any particular coordinate system. Our vector equation that we have is independent of any coordinate system. It can be any coordinate systems. Say for example spherical polar coordinate systems or cylindrical coordinate systems. The only thing is that the coordinates has to satisfy the orthogonality relationships. Correct? Then the coordinate systems need not be even Cartesian. So vector equation can always be expressed in some particular coordinate system, and to obtain a numerical result we must ultimately express the equation in some specific coordinate system. Now you can have any coordinate system, but at the end if you want to do some numerical calculation you should use the components. Now this definition is subject to the generalizations. This definition we can even generalize, and that will open up the new branch or the branch of mathematics which is known as the tensor analysis. Okay. Now let's try to summarize this. Now, this space of vectors is defined as a vector space. So, suppose if you have a collections of the vectors, suppose if you define three numbers, that is the component of the vectors. For example, if you consider a real number x1, x2 and x3, which is the vector x bar, xn is nth component of the vector x bar. The collections of all these vectors, now this is basically a three-dimensional space, but the collections of such vectors form a three-dimensional real vector space. Okay. Three-dimensional real vector space. So we ascribe 5 properties to our vectors. Suppose if we have a vector, say x and y, and y bar is equal to y1, y2, y3. So first thing is vector x bar is equal to y bar if their components are equal. Vector addition means their component also adds. Scalar multiplication means you can multiply with the scalar. If you multiply scalar, the vector will be multiplied. You will have to multiply the scalar with each component. Then you have negative of the vector. It is like multiplying the vector by negative number, negative 1. There is a null vector, means 0 vector. So these are some of the properties of our vectors. So first property is x bar is equal to y bar, means xi is equal to yi, or I here is 1, 2 and 3. Then second property is basically vector addition, that is x bar plus y bar is equal to z bar, means xi, so xi plus yi should be equal to zi when I goes 1, 2, 3. Scalar multiplication, that is a into x bar should give you, that is more like you multiplying the scalar with each number, that is with real number. You have a negative of the vector, so negative of the vector is defined as minus 1 x bar, which is minus x1, minus x2, minus, and then you have a null vector, that is zero vector, also is defined as one of the properties. So this is the vector addition. This is equality. This is addition. This is scalar multiplication. This is negative of a vector, and this is null vector. Since our vector components are real, the following properties hold, and that properties are commutative, associative, and distributive. So properties goes like this. So vectors are commutative. X bar plus y bar is equal to y bar plus x bar. Are associative, that is x bar plus y bar plus z bar is equal to x bar plus y bar plus z bar. So this is commutative, associative. Then you have distributive. Scalar multiplication is distributive. Or a plus b x bar equal to a x bar plus b. This property is called distributive. And also you have scalar multiplication, that is scalar multiplication. Null vector is unique as is the negative of the given vector x bar. These are the unique vectors. Remember, negative of the given vector, so idea is clear in this particular case.
Yes, sir.
Now we can proceed for the scalar or dot product, the vectors.
So I have a class from 11 to
Yes, that is a tutorial.
Yeah.
We will. So
It's working perfectly.